Alrighty, so we're back with another one. Hello and welcome. We got monotone increasing digits. I guess we'll get right into it. I don't even know. I was thinking about, like I was mentioning about writing a configuration file to generate random test cases, but we won't have to do that just yet. I think it's maybe better to practice without that. And the reason is that it might be better to practice without that, and the reason is probably because, like, during interviews and whatnot, you really don't have that ability, so you gotta practice testing without that. So maybe I shouldn't do that, but it is, it could be an interesting thing to do in the future. The integer has monotone increasing digits if and only if each pair of adjacent digits x and y satisfy x less than or equal to y. Give an integer n, return the largest number that is less than or equal to n with monotone increasing digits. Oh, okay. Well, that's interesting. So from left to right, it's monotone increasing. So 9, 1, 2, 3, 4, 3, 3, 2. Oh no, excuse me. It's from right to left. No, yeah, left to right, monotone increasing. So I would say this is an interesting question. Probably. Well, if the number itself is monotonically increasing, then you return it. But there's got to be a way to derive. How are you doing? Yeah, okay. I don't have an answer immediately, but the way to derive would be. Whoa. Oh no, I guess I touched my face, man. I've been doing that frequently. Touch my face and cause acne, and then I'd damage it further by touching it further. So I guess you need to look at the first two digits, because the tricky thing is any digit that we select, we need to have all the other digits that follow be greater than or equal to the digit that we place. So maybe we should go through some examples. So, like, I don't know. Let's do like 100. See if we can see some pattern. 1,000 is probably 999, right? Because we can't use a 1, otherwise, we'd have to have all 1s after that, and that's too large, right? So actually, I guess with each character, you have to check to see if it's possible to use that digit and all the other digits following. So if you had like 565, right? If you want 5, you need to know that 555 is less than or equal to this number. Oops. Okay. Yeah, so we could take 5, because 555 is less, we can use 5. Can we use 6? Or any number in between? Any of the numbers in between 6 and 5 is the same deal, so we can't do 566, that's not larger, so it can't be 6, so we can only do 5 here. So 555 is the best we can do. I think that's the general algorithm. I think that's relatively straightforward. I think it's not too bad. So we can do, like, let's do a random string of digits. So 2, 2, 2, 2, 2, 2, 2 looks fine. And the tricky thing though is that, like, let's see a 2, 2 here. Right, so you could do 2. 2 is smaller than all of the following digits. However, let's say, okay, so this, alright, so this one, you could do 2, 2, 8. I think the best you could do is 4. Right, because 4 is the smallest of all of these, and then 4 again. 4 still works. Can you go up to 7? You can't, because if you go to 5, right, you can't do. Well, no, that's not true. You could do 2279999. That works. That works. Let's actually try to figure this one out. So the reason you can't do 8 is because 8 doesn't match 4, but you could do 7 and No. Yeah, you could do 228, but the problem is that you can't go below 8 after this, and this will be too high. Yeah, 2 is fine. I guess really don't have to care about it. You don't have to compare to the next digit, I think, right? Because if you do 2 and 2 is okay. You can go, you have any digit between 2 and 8 works for 8. But the problem with that is the next value for 8 is too high. So you can't actually pick 8 there, so you get a 7. So I guess the question is, interesting, I don't know. I think you can do something iterative here though. So let's say you take the first digit you're looking at, and you have to say, okay, is 2 is all the way across, is that going to be, excuse me, smaller? It is, so that's fine. So you can pick the first 2. And how big are these numbers? They only have 9 digits, I think. Yeah, so this is fine. You can do a quadratic time algorithm, I think, where you check, okay, this digit, we could take the largest digit possible and just check if we pick that digit all the way across, what number would we get? And is that smaller than what we're looking for? And if it is, then you can take that for the next digit. So that next highest you can pick is 2, and again 2 all the way across works. You really can just check if the digit is well, I guess you do have to check it all the way across, because if you're equal, then there could be a point where this value is smaller. So really, as long as the number that you're looking at is greater than or equal, then you're fine. Actually, as soon as one of these numbers are larger, then you can stop, right? You have a slight optimization here, kind of terminate early. If they're equal, then I think actually you just take those numbers as they, like, you can also terminate early there too. So I think you can make this linear. You can do some optimizations to make it linear, but again, we're dealing with 9 digits, so it really doesn't need to be that efficient. But anyway, so basic idea is, can you check 2 all the way across? You can. Can you check 2 all the way across? You can. Can you check 8 all the way across? You can. Can you check 7? You absolutely can, right? Because, and really, as soon as you're below 1 of these values, then you could stop early there too and just say 9 all the way across, because that's the best you can. That's the largest number you can get, and we know it'll work because we're already 1 below, so you can just fill it with 9s after that. Another optimization. Not really sure if that's entirely, necessary, I guess. Yeah, as soon as you find a number that doesn't work, you can just decrement by 1 and then add all 9s. I think so, yeah. Okay, let's try some other random ones. 9 all the way across doesn't work, so you can't pick 9. So you can do 8 and 9's all the way across. Yeah. Interesting. Alright, how about this one? 3 is fine. 7 doesn't work. 6, 9. I think that's it. I think it's that simple. I think it's that simple. I don't know, man. I get this sneaking, uncomfortable feeling that this might be a little bit harder than I thought. Man, let's talk about Christianity. You want to talk about Christianity? Praise God. Today's the Lord's Day. Praise God. You mentioned it in your first video. I did? Oh. Yeah, Christianity is phenomenal. Are you a Christian or are you just a heckler? Also, you don't have to shout at me. I think we talked about this. You don't have to all caps me here. I can hear you just fine. I need to do that. So I think as long as the digits themselves are increasing, then you can just keep. If the digits themselves are increasing, then you can take the or greater than or equal to as you go. Then you can just take those digits until. So I guess if they're increasing, you can take those digits until, well, not necessarily, right? Because you could have like 2, 3, 8, 9, 2, 3, 4, 5, 6, 7, 8, 9, 0, right? So you can take 2, 3, 4. No, you can't do it 2 all the way across because the 0 at the end. But no, but this will be 2 all the way across works because even though this is larger, this is still smaller than this number. That's tricky. That's very tricky. You do 2, 3, 4, 5, 6, 7, 8, 9, but actually you can't do 9. You have to go to 8, 9. Hey, you can do that. That's fine. That's fine. As soon as you have to decrement by 1, you could just fill it with 9s at the end. So yeah, you would just keep incrementing your digits to follow the increasing digits, and as soon as there's a drop, then you decrement by 1, and then fill the rest with 9s. And I think that's the algorithm. I think that's sufficient. Alright, so we're going to build our integer. So we'll say break the integer into digits. You could do this probably I'm just thinking here. You could actually probably do this all in one shot, but actually we want to go left to right, so we do kind of want to have a vector of digits. Let's do that. And again, we're dealing with a very small number of digits, so I think we'll be okay. I don't think we really need to worry too much. So we'll say n is for n greater than or equal to 0. This is a tricky thing also. We can do n greater than 0. We're going to say digits.pushback n divided by 10, and then update n, divide equals 10, and at one point it'll be 0, and we just digits.pushback. Once we're greater than 0, you could do something like greater than or equal to 10, right? And then it's modulo 10, by the way, not divide by 10. And then, yeah, something like this should do it. Yeah, n is 0, this should be fine. So we're not going to check to make sure that n is unsigned. So break the integer into digits, and the most significant digit will be in the back, on the right side of our array. And we want to say, take the tonically increasing digits until aren't non-decreasing. It's not increasing, non-decreasing. And give me just a moment here, chat, because I want to focus. So we're going to say from right to left. So we'll say int x is going to be digits dot size minus 1. X is greater than or equal to 0. So it's x. Int val is going to be digits of x. If So to be monotonically increasing, we could say Boolean initial equals true. So if initial, otherwise, and we're going to say current val is -1. So if there's an initial value, we're going to say current value equal to value, and we're gonna add ret. Now the tricky thing is we're going left to right, so yeah, we are going to do maybe something like this. We're going to update our current value. Oops. All right. Doing a few things at once here, so this can get a little bit confusing. So if it's initial, we update. Otherwise, we set initial to false. So we're going to kind of guard our value. Otherwise, we set the current value. So we say check for excuse me, monotonicity, desired monotonicity. We'll say if val is less than or equal to current val. No, it's going to be greater than equal to val is greater than equal to current val. Then we're going to update current val equal to val. And what we want to check is we keep going now. We want to look ahead as well, because yeah, so that's a tricky thing. So this, I guess this technically is the look ahead. If the val that we're looking at now is greater than or equal to current val or previous val, it's probably better. And maybe previous value is what we want. Let's do it this way. Put this over here. So if this value is greater than or equal to the previous value, and then we're gonna always, I think, update this previous value to the value. Actually, that's not necessarily true. I don't actually know exactly what I want to do here. I'm not shouting at you, hey man, how are you? All is well, thank you for asking. All is well. How are things on your end? Just thank God for another day. Thank God for another day. This is kind of tricky. There are a few things to do here. So check for the monotonicity. If the monotonicity is fine, then we'd set, again, we're gonna set our previous value. I think what we're gonna do is we're gonna optimize this a little bit, like clean it up afterwards. So we're gonna set the previous value to value, and we're gonna say ret equals 10 times ret plus the value, and continue, right? Otherwise, though, we're going to say otherwise monotonicity is broken. We we're about 20 minutes in. It's fine. Take one less than the. Now there could be a problem here, right? You could have, it could be a 0. Look at this algorithm now, realizing. What if the next value is a 0? Like this. And we can't go to -1, 9. You really do need another look ahead, don't you? Yeah, you need to look ahead. Use a one digit look ahead. Okay. Now we're going to say we'll come back to this initial. We might not need that, or this previous value might not need that either. Yeah, so, okay. Monotonicity using a look ahead. If the look ahead is less than or equal to the value, excuse me, if this look ahead is greater than or equal to our value, then we can say ret equals 10 times ret plus value. Otherwise, we're going to say ret equals 10 times ret plus value minus 1. Now again, what if we have all zeros or something? So this one we know is 799. But what if we have 1, 0, or... Well, the thing with the zeros is you never have a leading zero, right? Because that's kind of the thing. It's like, you get something like that, but no. Okay, that's kind of useful. It's kind of convenient for us. We don't never have a leading zero, so we can always decrement by 1. Fill the remaining digits with 9s. Excuse me. So we're going to say for x greater than 0. Also did this wrong over here. This should be decrement x. That's a subtle thing. What do we want to do? So x greater than or equal to 0, we'll say ret equals 10 times ret plus 9. I don't know, do we need any of these other things? What happens if we do this? This seems simple enough. I don't know, let's test a couple cases, I guess. Let's see. 9, 9, not quite what we're after. 23 minutes, okay. That's close. What were some of these examples that we had? Well, we could just try some random numbers, right? Excuse me, so... that's interesting. Huh. That's a very tricky thing. So if the look ahead is a 0, we only really need one less digit if if the first value, yeah. Ensure that if the first digit is 1 and the next use less, one less, no result. So if, that's very subtle, but yeah, that's one thing. So if the value, excuse me, value is 1 and look ahead is 0 and x is equal to digit.size minus 1, and we decrement x. Very subtle. Hello, how's it going, Sahil? Welcome back. Hello, hello. Oh. I made a mistake. Oh, I forgot we had all these test cases. Come back to these in a moment. Give me just a moment. I'll explain what we're doing here. I'm just gonna focus for a moment. Oh, it works there. Okay. And then what about these other test cases? Which one of these is causing issues? Is the question. Oops. Sorry to bother you again. If you have a specific time for live practice, I'd love to practice questions alongside. Yeah, sure. I kind of do it randomly. I have to admit, I do it kind of randomly. Maybe I can, because I've been interviewing. That's the thing, is I don't. My schedule right now is pretty random. Basically, I'm leaving as much space open for scheduling interviews in the future. So I don't know how long it's gonna last though. Like I think probably at most a month from now. After that, I should have something stable. Not that I can like force anything, but basically, what's gonna happen is either I find employment or I start looking for jobs that are not necessarily software developer jobs. And then if I don't find any job, then I starve to death and go homeless. So I don't anticipate I won't find any job. We just still live in a country where you can find work, or I still live in a country where I can find work. But at some point I'm gonna have to focus very hard on finding work. Right now I'm technically focusing on it, but I'm also not looking. I'm not looking for just any job, because I don't want to. Not looking for just any job because I don't want to sell myself short. So I suspect this is the one that's causing issues. Let's see. Let's see what we get here. But I appreciate you mentioning that, though. I'm grateful. I would like to do these problems. That's something I think is good. If you want to do them alongside me, that's an honor. So thank you for that. But forgive me that I cannot reasonably satisfy your request as of the time being. But give me like a month or so, and I should be in better shape. Should have a full-time job, and then could make a set could make a set schedule. So my question is, what number was this? This is, all right, let's look at these two numbers here. Or we'll do it the other side here. Why are we getting a overflow? Oh, I know why. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so this is more than can fit. Uh, 1,000 million billion, 10 to the 9th. Okay. That's interesting. Oh, that's very interesting. Okay. So, excuse me. This should be it. Actually, just should stop there. It's actually going a little bit too far. Um, hmm. Actually, I think you're supposed to decrement x in all cases when you do this, because you select a value. Am I crazy here? Let's see. I don't know. What happens here? Okay. I don't know. Feeling like maybe I did something wrong here. Okay, we got one wrong answer. That's, like I said, feels like I did something wrong. I don't quite know what I did. Let's find out the wrong answers to see which ones are incorrect. Oh, that makes sense. Great, man. Wish you good luck. Thank you. Thank you. Talk to you soon. Talk to you soon. Now, which ones are wrong? Let's find out. 1, 2, 3, 4. 1, 2, 3, 4. Oh. Quite a few of these are wrong, huh? 1, 2, 3, 4, and 3, 2, 9. These ones are incorrect. Did something wrong. Let's see. How are we doing on time? 33 minutes? Okay, not great. Alright, so this is incorrect outright. Interesting. Okay. Yeah, you can't decrement below. Yeah, okay. Okay, so a single look ahead's not enough. I was thinking that. I was wondering if a single look ahead would be sufficient. It seems a single look ahead is not sufficient. Yeah, so 3, 3, 3, 3, 2. We can't do all threes. That won't work. We need twos. In fact, if you went to 0, you still need all twos. The first digit would need to be smaller. I think the issue is that you need this decrement here needs to make sure, well, as soon as you decrement something, excuse me, this is so tricky. Oh no, oh no, no, no. Trying to optimize things, I guess. Okay. So, yeah, I guess the first thing to do is for the first, and actually, this is incorrect too. It's not all twos, it's 2, 9 all the way across. This is the largest. So really what it is you want to see can this digit be written all the way across for 3? So the digit itself, so can you put 3 all the way across? And if that is less than the integer you're looking for, then that's okay. But in this case, it's not. So you can decrement by 1 and fill with 9s, right? But the tricky thing is, so even if you had like all 1s and a 0, you have to actually go to 0, all 9s. I actually think this case is handled correctly without this extra part. Yeah. But the question is, where or why? There's some issue here of like, of course you'll be able to decrement, but like what if you have, 2, 1, 1, 1, something like this? Well, you can't use 2 because there's a 1 there. As soon as you see something smaller, you won't be able to take this digit. But what if you have 1, 2, 3, 4, 3, 2, 1, right? So 1 you can use. But then what about the next value, 2? Excuse me. Well, 2 you can use. See, that's a tricky thing. I think if the numbers are increasing, then you're okay. You can just keep increasing, right? So 1, 2, 3, 4. But the look ahead, if it's not increasing the look ahead, then you need to check further ahead. That's the issue. Yeah. So the look ahead needs to be for each digit, and it's going to be, is every digit, is each look ahead digit, is it increasing, or are any of these digits increasing, or if they're equal, you keep looking ahead. If they are decreasing at any point, then you have an issue. So yeah, so I think that's the way to do it. So that's pretty subtle thing, but it's, so you see if the 4 is increasing, so you take 3. 3 is decreasing from 4, so you take 3 and take 9 all the way across. But if you see something like 1, 1, 1, 2, 1, 3, 4, 2, right? 1, you can see the look ahead. 1 is this look ahead. It's not increasing or decreasing, so you go to the next one. Not increasing or decreasing. Next one is increasing, so you could take 1, and again, actually I would say all the way up to the, excuse me, you can actually generate the number all the way up to the first increasing value, and so you would say 1, 1, 1 all the way up to 2, and then now you check on that value for 2, and you say look ahead is 3, so 2 is fine. Look ahead for 3 is 4, that's fine. 4's look ahead is actually decreasing, so you take 1 less than that value and fill with 9s. I think that's the algorithm to go with, but you could have like all 1s all the way across, and actually that would be the value to take. That if it never increases, then you just finish right there and return. If it never decreases or increases, that means that all the values after that are the same. Yeah, you would build this integer and then complete. So yeah, so if your look ahead makes it off the edge, then you're done. But yeah, the look ahead itself, if you reach an increasing value, then you can take all of the digits that you've processed. If you reach the end, you can take all those digits. If you reach something that's decreasing though, and you don't reach either of those other two cases where it's always equal or something is increasing. If you reach a decreasing value, that means that the digit you're looking at, you cannot take. You take one less than that and then fill the rest with nines. So a pretty interesting question. I think it's still linear in the number of digits, but it's, yeah, I don't know. I'm trying to do this like, I guess hyper efficiently, but in terms of the algorithm, but it actually doesn't need to be that efficient. Like, there's only 9 digits to work with, so it's it's kind of straightforward, I guess. But you could do something like this. So we'll have a look ahead and there's 1 digit forward. Or actually we have the value. We're going to process look ahead values. Is greater than val, then we can to that point yeah, something like this. So we're going to say int current equals ret. We're going to say for int look ahead, which is going to be digits of, we could say int, I guess we'll call this some index j. We'll call it j equals x plus 1. J is less than or greater than or equal to 0. And yeah, we'll do it that way. And decrement j. Int look ahead equals digits of j. Then we're going to say it's x minus 1, by the way, not x plus 1. And then we're going to say current equals 10 times current plus look ahead. We'll say if, so here we go. So if look ahead is greater than value, do the following. So we can actually just break here, I think. Right, we could say red equals current and break. If, or, well, we can do greater, let's do greater than or equal to -1, let's say. Well, okay, so if we say less than or equal to -1, or digits of I of j, yeah, we'll do it this way. Something like this, I suppose. So if this digit is greater than value, then we want to set ret equal to current. Now, the tricky thing there is I have this digit that we're looking at. We have this look ahead. Trying to decide whether or not I want to take this digit. I guess you could just add this part here. I don't know. I'm trying to. Yeah. Now, yeah, we run off the edge. We can do this if we. This is a little bit confusing. I don't particularly like how this is written, but it's okay, I guess. So, look at it is equal to value. And then we continue processing look at digits. Just keep going. Look at it is less than value, then we take val minus 1 and fill the remaining digits with 9s. So we'll say ret equals 10 times ret plus, val minus 1. And then we have another for loop here. Decrement x. Say for, this is x is greater than 0, I think greater than equal to 0, and we say the same here, and actually you could even return, excuse me, you can even return here, yeah. So what would happen here? X would exit. So you would exit this loop. It says x greater than 0. I think it's x greater than equal to 0, probably. And yeah, I mean x will be set to 0 at the end of this. I think that's it. I think that's all you need to do. So if you, so if you are greater than this value, this look ahead, then, part of that too is you have to update where x is as well. Because you decremented j and x, so you actually set x to where, I think x becomes j. So let's say you read everything, including the, like, all 2's all the way to 3, like 2, 2, 3. So you would go, 2 is the digit, look ahead would be 2. So this is interesting because I think you actually current would be 10 times ret plus val, potentially. Now, not necessarily. Yeah, actually I think that's fine, because this here we update ret accordingly. We don't take current at all. But we do have this look ahead here. Yeah, and if we look ahead and we find that we're less, then we have this case. Yeah, we update ret accordingly, but okay, I think that makes sense. So if we had all 2s, we'd start with 2 here. We have this look ahead. It is a tricky thing though, because, well, no, this covers if you go off the edge. That's fine. That's fine. If there's no other values, then you would update to red is just current, and that's that. Okay, that's fine. So, does this work? I don't know. I'm not really thinking it all the way through. Okay, it's wrong. 1, 2, 3, 4, 3, 3, 2. Alright, 1, 2, 3, 4 we got, but 3, 3, 2 is wrong. Really? Current equals 10 times ret plus value, which would be 3. So, yeah, we process 3, 3, 2. So we start off at 3, we have our look ahead, we increase to, this goes 3, 3, and then we say look ahead 3 is not greater, it's equal, we would continue, we go to the next value 2, j squared is 2, we see, right, 2, okay, so look ahead is 2, oh, I see. So this is false, but this is also false. So we should hit this point. What is happening? Excuse me. Also, we're spending a lot of time on this. Yeah, I was expecting 229 actually for my code. Why do we not get 229? Maybe we can print J, index J. We also want to see, well, let's just do that. Excuse me. -1, 0, -1. Okay, so it starts off at 1, current is 3, look ahead is 3, current becomes 33. Now we print, and we get to 0, and J is 0. What's current? That should be 332. Yeah. Okay. What's the look at and what's the value? Expecting this to be 3 and 2. Yeah, okay. Look at is 2, value is 2. So this is not true. Look at is 2, value is 3. Right? Excuse me. So this is false, so we end up here. Oh. Oh, okay. We do need that line there. Yeah, okay. That's a bit subtle. Yeah, okay. If you don't include that line there, then you actually end up down here. And yeah, okay, I get it. I get it. That's fine. That's fine. No. No. This one, huh? The only one. 3 from the bottom. Did I have is my logic wrong? Uh-oh. Uh-oh. Oh, thinking here with the look ahead. I don't know, probably doing something wrong. So 6 7 6 7 7 9 9. Not correct, right? It should be 6 6, right? Oh man, this is taking forever. 6 7. This look ahead is greater, so we could take 6. So now here's the question: do we take 6 and 7? No. No. Well, can you take all the way up to that digit, including that digit, or is it? I think that's part of the problem here. I think you don't include that digit when you see this greater than value. Yeah. Okay. Let's say interesting. I don't know. I don't know. Yeah, you don't necessarily include this digit. Yeah. I see. I think you do include it afterwards, though, after these if statements. How about that? What happens there? 6 6 7 9 9 9. Wrong. Okay. No. The logic is so hard. All right. So if you see a greater than, then everything except for everything except for that look ahead can be included. So you keep collecting. So it's really just this one where if it's equal, you would keep going. It's kind of the equivalent thing here. there were some problems here. So current includes this value initially, right? We're trying to figure out whether or not we want to select this first digit. And then we say, look, we take a look ahead, and we say, look ahead is going to be the next digit, so 7. We say look ahead is greater than our value. Then we can use 6, and we did. So use 6, use everything up to that look ahead. And I think it's not J though. So there we would break and we would say ret is now 6. J is too far. We now processed 7, which is not correct. That's not what we want at all. We really want that to be before J. Or there would be J plus 1, I think. Oh, there we go. Okay. Okay, that looks pretty good. Let's try some other random things. Oh boy, that's too many. Alright, how did we do? Quite a long time on this one we spent. Should we go for it? I forgot to use 0. Oh, we got it. Okay, sweet. 2 milliseconds for this. Really? Hey, there we go. We got 100%. We used more memory though because we pushed our digits here. I guess we could. I guess technically you could interweave what we're doing here. No, I don't think so. Actually, I think it's better to break up the digits first and then. Excuse me. I think it's better to break up the digits and then process. Yeah, that was pretty rough, I have to say. That was pretty rough. I don't know, man. I don't know what to say about that. I guess in an interview I'd probably do this a little bit more, what I want to say, hold on. Yeah, I guess what I want to say is a few things. So in an interview I'd probably do a little bit more brute force and do like instead of doing this look ahead approach here. By the way, this is linear in the number of digits. That's kind of why I was trying to code this in the way that I did. I was trying to get it to be more or less optimal in terms of time, hence the 100%. But I think even if I didn't do it optimally, I'd still get a pretty good time. The thing is, excuse me. The thing is, what I was thinking was, yeah, again, it's pretty rough. There's like a few different pieces involved here. So there's like a few cases, few issues. It's linear, but I spent a lot of time trying to make sure that it was linear in the number of digits, as opposed to quadratic in the number of digits, which would have been pretty quick too, fast enough to solve the problem. Yeah, during an interview, I'd probably do quadratic time because it would just be, it's quadratic. It's logarithmic in n, just log square in n. It's fine, I guess, in some sense. The issue is that it's just a lot harder to code the linear in the digits solution. As you see here, it's a lot harder to think it through as opposed to the quadratic time. The quadratic time algorithm, I think you literally would just, when you select a digit, you either select the one in front of you and then I guess you would check if you just continue with that digit all the way across to the end, if that's smaller than the digit you're looking at. If it is, then you can take that digit. If it's not, then you're going to take one less than that digit and fill the rest with 9s, and then you're done. Yes, yeah, that's pretty much it. That's pretty much it. That logically, it's a lot simpler to code, I think. Logically, it's a lot simpler to express and think about and program it. Here, in this case, really what you got to do is you got to say, all right, we have a single digit that we're considering, and then we're going to look ahead to find out the first time that we find a value that is either smaller than this, or larger than this, or equal. If the first value we see, we're going to check the next value. We're going to continue to iterate depending on what happens, but the next value, if it's smaller, then that means that we can't monotonically increase from here. So we would take one less than the value we're given and then fill the rest with 9s. We're done. If we are equal, then we can keep iterating until we find something that's not equal. But the thing is that depending on what we find, we want to potentially include the things that we saw that are not equal, or potentially include the things that we saw that were equal. So if we see something that's greater, then we can say we can include all of the ones that we saw that were equal up to this point, and then continue to iterate, continue to repeat, because that means that all of those digits would be valid. That we can always we basically our solution is going to be greater than or equal to. We just added all zeros to the end. We can know with certainty at this point that our solution is greater than or equal to that. Excuse me. And so we can kind of just reiterate from there. That's if we find something larger. If we find equal, then we keep going, and if we find less than, then we can, at that point, we can just decrement the value we're looking at. Since the last thing we looked at, the last value that we considered, either there was no value or the value itself was a greater value. That means that decrementing that value won't break the monotonicity that we're looking for. So that's why the decrement works nicely. And then also filling with 9s, our algorithm finishes right then and there. So yes, that works nicely. So basically the invariant state at each point is kept. But like that's not a very clear or concise way of expressing that. Like it's very awkward. This whole thing is awkward. I also don't like this part where I have like a declare variable, and then if we can, we fill it, and then if not, then we don't need it, but it's not filled, and I guess it's okay, but it's not my favorite thing. So yeah, kind of involved, man. Pretty involved. Yeah. So. Yeah. Interesting. But that'll be linear overall. All right, let me go. Thank you for watching. Talk to you soon. I need a bit of a break with my voice. I was not expecting this to take an hour, but it took a while. Yeah, thanks again for watching. Talk to you soon. I guess, I don't know what I'm doing. Maybe we'll do another one? I need a break. I don't know what I'm doing. We'll figure out what we're going to do next. But yeah, thanks for watching. Take care. Take care.